Thank you, Andre, and thank you also for the opportunity to present here. We will talk now in the next 20 minutes about equity-linked life insurance policy. So we have an equity-linked life insurance policy with guarantee. This means we have a product which is linked with the equity. This can be a stock or a mutual fund. And of course, the stock price through time changes its value, and it is possible that at the expiration time T, the stock price is lower than the guaranteed value of the policy, which is G denoted here. So of course, in this case, the insurance company suffers a shortfall. And for these kind of cases, the insurance company would like to hedge the risk. So the presented results were published a few years ago in the Journal of Computational and Applied Mathematics, and this is the joint work with Michael Perman. So what was motivation? Equity-linked life insurance policies have seen an increase over the last decades, but of course, for products with guarantees, some of the risk is transferred back to the insurer. Risk management has to follow regulations. Insurers have to calculate sufficient policy reserves to hedge the risk. But with the advent of Solvency II, companies have more flexibility in how to hedge. So the first question was which tool to use for hedging the risk. And we decided to use options. So in this presentation, I will present the hedging strategy that we proposed. Boyle, Brennan and Schwartz have already in the late 70s recognized that the payout of equity-linked products with guarantee is linked to the payout of certain options. And what is an option? An option gives its holder the right, but not the obligation, to buy or to sell a certain amount of financial asset by a certain date for a certain exercise price. Let's say if we would have a European put option, if K, which is exercise price, is lower than ST, which is price of the stock at the expiration date, there is no interest in exercising the option. But if K, exercise price, is greater than price of the stock at the expiration date, then the holder makes a profit of K minus ST by exercising the option. Okay, so we decided to use options, but what kind of financial model to use was the next question. So of course, we decided to first approach with the most simple one, and this is the discrete time model. So Cox-Ross-Rubinstein model is discrete time model with two underlying assets, a bond with price process BT and a stock with price process ST. So the initial price of the stock is S, and then it can be multiplied by the factor U with probability P and multiplied by the factor D with probability 1 minus P, and this actually we will do for every step. So we can represent our stock price with the binomial tree as here. And then, of course, we take a random walk or random process to walk over this tree, and it is a homogeneous Markov chain. Okay, so we have now a model, and we know that we would like to use options, but how to decide when to buy options or even if buy options? So we would not like to consider the case that we buy options at the start, but we would like to consider it through the time process. So if to buy options and when is the best time to buy options if needed. And in this way, so hedge the risk of shortfall. So for this when question, we use the Snell envelope. So if we have an omega Fp, the probability space, and filtration Fn, so what is a Snell envelope? We should have an Zn adapted sequence of random variables, then the sequence Un, which is defined as U capital N equals Z capital N, and Un is maximum of Zn and conditional expected value of Un plus 1. This sequence is called a Snell envelope of the sequence Zn. And what is the optimal stopping time? So this will actually help us to determine when to buy options for our case. So what is an optimal stopping time? A stopping time nu with respect to the filtration Fn is called optimal for the sequence Zn if expected value of Z nu is a supremum of all expected values Z mu over all possible stopping times mu. So actually, it's when the expected value is supremum or maximal. So we are maximizing the expected value of our sequence Z. Optimality theorems gives us that a stopping time nu is optimal if and only if Z mu nu equals U nu and the stop sequence is a martingale. So when a stopping time will be optimal, if we go one step back, when UN equals Zn, and even more further on, so corollary gives us that there exists an optimal stopping time if and only if this mu zero is finite, and where this mu zero is the smallest of all n's, where UN equals Zn. So the stopping time mu zero is then the smallest optimal stopping time. So it will be when we will go in through the binomial tree. So the first time that will happen that UN equals Zn. So this is the theory. And then let's first look one small example to see how this optimal stopping time works. And then we will go to our simulations. So let's see the Snell envelope on a rooted tree. So we have a finite rooted tree. We have a function f which assigns a real number to every vertex. All edges from a vertex to lower level vertices are assigned probabilities that add up to 1, and the random walk on a tree is a finite Markov chain. So what kind of sequence we will have that we would like to maximize the expectation? We will have this zk, which is 1 plus r, where r is the interest rate, to the minus k times this function f. So we would like to look for stopping time mu, which maximizes the expectation of this zk. So in more colorful language, a random walker on the tree will decide when to pick the number at the vertex in such a way that the expectation will be maximized. And this can be nicely be seen on this case here. So as you can see, we have a binomial tree here, and the values are written in the circles. So the values on each vertex. You can see that there are zeros. Only one value is 1. So we would like to catch this 1, right? So we define, we are going through this binomial tree with up with probability p, which is 0.49, down with probability 0.51, and Zn is this function, so with these values. And Un is then the Snell envelope of this sequence. Just for the sake of simplicity, we define the sequence Sn, which is Un minus Zn. Just recall that the stopping time is optimal when Z mu equals U mu. This means that this S value of this S should be 0. So we are looking for the first time that this sequence Sn will have value 0. So if we start in the root of our binomial tree, and let's say that we go up and down, you can see that here the value of S is 0.6, which means that we did not reach the stopping time yet. So in our case further on, we should not buy our option yet. Why not? Because as you can see here, 1 is still available to us, right? There is still hope that we reach 1. But when we will reach 1, we stop here. So this is our optimal stopping time. The second case would be if we start here again at the root, we go 2 steps down. We cannot reach the value 1 anymore. So here is the stopping time. So in our, again, later on case, this would mean buy an option. Okay, so this was just small example to see how the optimal stopping time works, and now go to our model. So what are our assumptions? We have M people, which are all aged X, all have identical equity-linked investments in an underlying fund with survival guarantee G and duration T. So this means that the people that survive this certain time period T, they get this guarantee G. So the first case was not including also the debt guarantee. The insurance company invests their total premium in one unit of the fund with initial value as 0. Interest rate is constant. Arbitrary put options with arbitrary strike prices and expiration dates are available on the market. So these were our assumption. What would be the guaranteed amount? It would look like this. So this means S0 times 1 plus R to the T. This means the interest rate times the initial value of the stock, or 1 minus C times ST, where the C is some share that insurance company takes for the management fees. Okay, so we said, okay, we will use this optimal stopping process, but the crucial part now is how to decide what will be our criterion when to decide when to switch to options. So which from our before theory, which sequence ZT should we define, right? So what will we maximize? So L plus here denotes the discounted shortfall for the insurer if there is no interaction with the derivatives. We have this kind of case. So what is this alpha T times G? This alpha T denotes the number of living policy holders at times, so different times actually, but here is capital T, so at the end, minus M times ST. M is here how many policy holders did we have at start. Then we should introduce two filtrations. One is for mortality, this is HT, and the other one is for the fund price or stock price, and they are independent. Conditional distribution of discounted shortfall L plus is equal to this thing. So again, alpha T has the distribution equal to conditional distribution. So this means that what are expected number of policyholders at the end. What is the conditional expected shortfall with respect to probability measure P? So we have here. So actually, this is the amount of money that we need to have at the end minus the amount of money we have or the amount of stocks that we have in our hands. Okay, because of course also the options need to be bought. We need to consider also the OT, which is the price of the put options, and we consider two cases. So how many options should we buy? This is K1 and K2, and I will speak of this just now. So what is K1? So first one was to consider to buy as many options as there is living policy holders at the time that we are buying the option. And the second one is to buy as many options as we expect to be living policyholders at the expiration date. Of course, this K2 is smaller than K1. And this is our crucial, so the sequence ZT, which is defined as here. So this is the expected conditional loss minus the price for our options. And this is the sequence that we would like to maximize. So we are looking for the optimal stopping time, which will maximize this sequence. So when the expected loss minus the price of the options is the highest, has the highest value. Okay, so when we did this, so the simulation of this, the question is now how to decide if our approach is good or not. What did we do? We looked at the final loss or loss at maturity, and we looked at both cases. So the case when we do not buy options, this is the case of no interaction. This case would approximately correspond to delta hedging, where the insurer at all times has to reserve an amount covering the difference between the expected present value and the current value of the fund. And our approach, which is switching to hedging with put options at an optimal time. Okay, so our input data where we have axis 30, which means 30 years old when the policy starts. The initial stock price is 1. It can go up by factor U, down by the factor D, with probability for up 0.49. Interest rate is 0.015. The expiration date or the policy is 30 years long. This management fee is 10%. We have 1,000, so M is 1,000 people who have this exact policy, and N is 5,000, means we did 5,000 simulations. For the mortality simulations, we consider the Slovene mortality tables for men aged X is 30. And here in this graph is the answer to the first question, which was is there even some stopping time? So is it does it exist the stopping time that is not 0? So it is better to wait. And you can see here, yes, the answer is yes. So there are some different stopping times here, still all quite near to the start of the policy, but still there are different in different simulations. And these are the final losses for the both cases. So the left one is the delta hedging, and the right one is our approach, so switching to option hedging, and you can see that are considerably better with our switching. Also here are presented different examples for different P's. Again, what is this P? Is probability that stock moves up. As you can see, if we consider like a pessimistic case, 0.48, it's better to buy option at the start. But if we are not so pessimistic, there are different stopping times to consider. Here are the distribution of final loss in the switching case for K1 and K2. If you remember, I said K1 is to buy as many options as there is living policyholders at the time of buying the options, and K2 is the expected number of living policyholders at the expiration date. So they are quite similar. The last case that I would like to present the results is also the minimum death benefits. So we considered also the case where the policyholders that die during the process do get some minimum death benefit. And also in this case, it can be seen that there are significantly different results for the distribution of final loss. So this is left one is delta hedging and right one is switching to option hedging. The stopping time, distribution of the stopping time is seen here. So just to recall, what was the main idea of our strategy? At time T, the insurance company compares the future conditional expected shortfall to the price of the options covering the guarantees for the conditional expected number of surviving policyholders, and the time U to purchase options will maximize the difference of the two. Advantage of the new approach is interaction with financial market, but of course we did have a lot of assumptions. Let's say the discrete model, arbitrary options available, constant interest rate, and constant mortality table. So all of these assumptions can be changed, and this is a lot of opportunity for further research. Thank you for your attention.
Thank you, Anna, as well. Clap, clap. Great presentation. So I open the floor to questions. We have about 2-3 minutes. Shikica, please.
Thank you, Anna, for the lovely talk. My question is mainly concerned with the company buying options. So have you, in your model, maybe considered some market fees, because apparently you can't get an option for free? Thank you very much.
Yes, yes, of course. The market fees are considered there. Yes, yes.
Maybe some other question? I also ask one, if any other has any, please raise your hand. Basically 2 short questions for Anna. Firstly, these parameters that you have to go up or down in a 3 are 0.49 and 0.51. What was the reason for precisely those parameters? Can they be changed? I assume they were calibrated. And just shortly to add, a bit more theoretical, why this form of binomial tree? Could any other, and choosing then the random walk as stochastic process, could any other shape of a tree be also chosen? You mentioned this at the end, but
yes,
what would change?
of course. So
Thanks.
the choosing for the binomial tree is the simplest case. We also consider the same P for every step, right? So we just wanted really to have an idea if this will work. So we started with the most simple case. So that's why binomial, because you have just 2 steps on every, so 2 options on every step. The second one was regarding the values for P. So as you could see here, if you go with a really pessimistical approach, of course you should right away buy options, because if you go down like by a lot, it's not realistically to expect that you will go up in the future, right? So it turns out that around 0.50 is the best way, also the best model to be for our approach.
Are there
So
any?
our approach is the best in this kind of model.
Thanks. Are there any more strict bounds here? You have 0.48 as the lower bound. Is there any result on the how spread this could be?
No, but this would be a good idea to check. Thank you. I will look into it. Thank you.
Thank you.